So for the convolution neural layers, there's two main modifications we will make. Just notation, I want to go from the input, I want to recreate this effect of a convolution in a very efficient way. And so then what you want to do here is you want to do a first modification. And the first modification is the idea that to know the result of the convolution for this neuron, okay, I don't need to know the whole image. I don't need to know all the pixels. I only need to know this little part, because my kernel, let's say my kernel is a 3x1 or 3x3, is applicable only on a subset of the image, okay? And so I only need to know a small subset. So I don't need to have all pixels connected. I only need a small number. So it's a very sparse. This matrix W, which originally connected everything, there's going to be a lot of zeros because there are a lot of pixels, like these pixels here. They have nothing to do with the output here. The second one, which takes a little bit harder to understand, but I think is the most important, is that there's a lot of redundancy. What it means is the kernel used here should be the same kernel used here, should be the same kernel used here, should be the same kernels used here. So this link here, which is the first of, let's say, 3 links, it should be, and it's swapped because it's convolution. If you wonder why this one is green and not red, it's just convolution being swapped. That's how the convolution is computed. But yeah, but the first one, like any of these neurons, the first one coming in, okay, this one, the first one coming in, we don't want it to be a different W3. We don't want it a different value for different part of the image. We want them to be tied together. We want what's called tied weights. This is not a free parameter different from this. If you make any change to this using gradient descent or something, the same change should happen here. In fact, you should sum all of these changes because they're all together. They should all be, they're all the same. You want to tie them together. And so that's the 2 key modifications. What it shows mathematically is that big W matrix that links all possible input pixels to all possible output pixels is an extremely sparse matrix because it's as large as what your kernel you want it to be. And also what's important here is the tying of the weights. The W1 is the same for the other W1. So the same same weights here. All of them are going to be tied together. And mathematically, what it means, I didn't put a slide for that, but what it means is gradient respect to W1 here is going to be sum over, like you're going to sum all of them partial 1 together. It's all tied together. So, and the nice thing with it is that it can be efficiently implemented. Because at the end of the day, I show it to you as a big matrix, but really as it is, it's implemented is all in parallel. So I can do each row almost in parallel all together. And that's why it's such an efficient thing to do. Okay, so this is the intuition behind CNN, the core component of CNN. This is this W matrix. The W matrix here, this W matrix, it will learn our kernel. So what's really cool is suddenly I take a multi-layer perceptron or fully connected, and then a normal neural networks, and suddenly I make it in such a way that it will learn from me a kernel. So the W is going to be a kernel. And now if I want many kernel, I can stack, and I'm going to show that in a little bit. But here you have one kernel that will be learned, and you can always get a little bit more fancy and then add an activation function after that. And this is back to the typical neural representation. But the most important part for the CNN is that convolution layer. That's what we will call the convolution layer. And we call it the convolution layer because it's a typical W. It's a typical, it's every pixel connected to every possible output value from the response map. But the key here is that because we tie the weights, we end up not learning all possible weight, but we end up learning a very small subset. So this big W looks really huge, but there's only 3 values learned in it. And you can see why the number of parameters is so good for CNN. Although you hear now with CNNs with like millions of parameters, but the basic CNN doesn't have, like, compared to how big the image is and how complex this could be, it has very few parameters compared to like the number of connection that could be from an image to a response map. So that's why they're also quite efficient. So convolutional neural layer, I talked to you about the 1D example because it's easier, but this can be expanded to 2D, and that's usually the typical CNN. It's not just a 1D vector that runs over, but in fact it's a 2D template, a 2D kernel that is going to run. So if it's a 3 by 3, what is the number of parameters in W? If I have a 3 by 3 kernel, my W, my huge W matrix that matches that links my input to my response map, how many parameters, free parameters in it? Only 9. Okay, only 9. So that's very few in this. And it could be also 3D because you could look over videos. I'm going to give an example of 3D CNN. It could be also 3D or multi-channel or 3D because you have your image is 3D in a sense. When you have a color image, you will often have 3 images stacked together. And so you will often use 3 by 3 by 3 kernels for this. And it can be expanded to multiple kernels. If you remember this image I showed of Haar and Gaber, there was a predefined set of kernels of template. And I showed you that nice comparison where CNN learns these kernels, learns these templates. And what you saw is like maybe like 64 of these templates. So really what a typical CNN will have many of these kernels that are learned. So I have my input image, and for the first convolutional layer, what I will do is maybe 64 kernels that will be, and they will maybe initialize randomly with the hope that they will learn something useful, each of them. And so what you will do is you will simply have many of these kernels, many of these W matrices, and you will stack these W matrices all together in one 3D matrix. So your input may be just 2D, and then a typical kernel will have a 2D big W matrix, but because it is over many kernels, then it will be a 3D matrix. And the response map, will it be 2D or 3D? It will be 3D because you have many kernels. You'll have a response map for the first kernel, a response map for the other. And so that's what you see. Your image here, you have a kernels. In this case, maybe there's, I don't know, 10 kernels. And what's very weird here is the size should be the same here of the number of kernels. So sorry for this. But yeah, you run this over the image. This should be usually the kernels. Here I show the huge W matrix. Often you will see the kernels being much smaller. And they show much smaller, they will show them just as 3 by 3, but it's a little bit, they only show 3 by 3, but in what really it represents is like a huge matrix of the size of almost a W of the size of the image. That's what the equivalent of what the convolution will be doing. Okay, so the convolution neural network, the typical one will have multiple layers. So I talked about these kernels for one layer. So for one layer, you will learn these different templates. And these templates, what they allow you, and that's what I show here. These are the kernels that I'm learning, these W that I'm learning. And then at the next level, I will learn. And in here, in this visualization, these are really kernels. At this level, I'm showing something, but in reality, you will rarely learn a kernel like this. What you will learn is a combination of kernel. It's kind of almost of a kernel of a kernel. So what it is you will have these edges, and these are your kernels at the first layer. And at the next layer, your kernels, you're also learning kernels or templates, are not going to be done on the image, which is a little bit what this visualization makes you believe, is as if these at the next level, they're just bigger on the image. No, in fact, the next level, often the kernel will be the same size, maybe 3 by 3. But instead of running on the image, they will be run on the response maps. And by running them on the response map, I'm kind of doing a kernel of kernel, or combination of response to the kernel. And then at the next level, I will also doing another kernel, which again is not going to be much bigger, probably also 3 by 3 or something like this. So it looks like the kernels are very big, and that's what I run. That's what I'm applying on the image. But here, what they did is a simple step of what's called deconvolution. This is one of the paper visualizing and representing CNNs was partially one of the steps was about deconvolution, to try to see what happens in the interpreting a little bit what happens in the CNN. But in reality, you have a kernels at each of these, and these kernels will relatively small, but because you have a hierarchy of them, they will get bigger. But how do you encourage abstraction and summarization? Because if I have an image of like 2000 by 2000 or 1000 by 1000, and I run and learn my kernels, and I get a bunch of response, and the response map will be about 1000 by 1000, and then I learn new kernels on it, and then my next response map is 1000 by 1000, and I learn new kernels on it, and it's 1000. But if I just do convolution, I'm not forcing the algorithm to summarize things or abstracting. And this is where the pooling layer comes in. The pooling layer is relatively simple. The idea is, and you have different type of pooling, which is you could just, one is mean pooling or max pooling. I think in the paper of deconvolution, I think they may have done max pooling, and that's often used. But the idea is I get my image, I run the kernels on it, I get my response map, and now I have still a big response map of 1000. And before learning my next kernels, what I will do is just pooling is just, you could see as a fancy word for downsampling. You are downsampling this, and there's different way to downsample or to pool or to downsample. And downsampling, the simpler one will be maybe mean downsampling, so you average them. But what the problem with sometimes with mean pooling, if you look downsampling, for example, if you do the downsampling of an image, then it may start looking a little bit more fuzzy. the edge will not be as sharp. So max version may be more sharp, but it will be more noisy. So you can see there's a trade-off in that. So this is the pooling. The great thing of the pooling, or at least has been done, is that there's been tricks that have been developed to make the pooling efficient also from a gradient perspective. Because if you start doing things like a max pooling, a mean pooling is maybe easier, but max pooling is like you have to be able to go backward and be able to differentiate that. So a step function is by default will be harder to differentiate unless you do a nice smooth version of it. And so there's been some approaches to do the gradient descent and passing the gradient even through pooling layers. This is just one example of that. So so then we have everything together, and that's what CNN is. A CNN and a lot of these libraries, sometimes they will call about layers. Okay, and you'll say you have your first layer is convolution, and then you have a ReLU. What's really interesting is, like, in the terminology of neural network, you need both of them to have a neural network, because you have the W. This is W. This is just multiplication by W. And then this is the activation function at the end, this interior, the nonlinearity. And so they will go ahead and they will architect. And I think the right word, architect, because there's a lot of human knowledge in this that need to be added on, like, what is a good architecture for this. And so we'll have different version and of this. Most of them, like a famous one is the VGG, which is one of the first popular one, which a bunch of convolution. And then you do a pooling. So that up to now, the response map was almost the same size as the original image. But as you go here, it should be smaller. And then you get, and then you, at this point, you will have what is the last convolution layer. So you have an image maybe of, let's say realistically 64 by 64 or 640 by 640. And by this, you may be to the point that it's only a size of 16 by 16. And then what you could do is, like, hey, now I have that 16 by 16, and I want to do classification. What is the object that's in the image? What's really nice at this level is that I still have information, like this response here of my 16 by 16, like this response here is related to this corner of the image. And the next one is related to this part of the image. It's almost a grid of 4 by 4 on the image. And so this layer, at this layer, I have a mix of the location of things and the appearance of things. The appearance is like the response map, and the location is because you have like 16 by 16. And so I will use this representation, which is very similar to a histogram of gradient in a sense. It's just that it's dynamically the kernel are learned. And then what I do is I put the MLP, multi-layer perceptron, on top of that as my classifier. So these are my input, and then I put fully connected layers on top with the goal of finding which of these are the most useful for each of the type of object. So this is a typical architecture, and a lot of them, one thing I want to say is a lot of them are trained on the same data sets. And you have to be aware of that, because a lot of these data sets go with maybe just 1,000 class labels. Some of the original one had maybe only 80 class labels. So they knew what a person was, but they don't know if it's a man or a woman, or didn't know like the age or something. Or they may know it's a car, but they don't know which type of car. They may know it's a cat, they don't know which. So they don't have, like, you will hope that because they look at all of these different types, that they see a little bit of the variance, but they were trained for very specific class type of object. And so you have to be aware of that when you use a CNN, that they may not emphasize the thing that you would like. And that's why there were extensions of VGGNet, like VGG face, that were just trained on faces as an extension. And this is the image I showed you earlier. You can see the kernels that are learned, the weights, and the different layer. And these are shown. I can show it, they're bigger, but these are shown because of deconvolution. They're not bigger, sample. They're just deconvolution of that, and not the best deconvolution. You will see some better deconvolution. And there's some approaches, and I'm not going to go as much in this because it's part of your readings. And if you don't read the paper, then you should ask the people who read it. By the way, the papers this week are about understanding CNN and RNN and really understanding why they're working and why they're not working. And so, there are a lot of different activation, different architectures that you can use and different variation. One of them that is worth discussing is the one that has a residual connection. So the kernel, the neural network, then its job will be to kind of say try to model what previous layers didn't manage to model, and let's just model what you didn't, what previous layers. And this skip connection or residual connection was also very important to make it possible to train a very large number of layers. That's also helped with the gradient in this case. So you can go and visualize these. And so that's the purpose of the papers this week. And so I'm gonna, because of time, I'm not gonna emphasize as much this next part about visualization. But either you read or you have your colleagues and talk about it. But deconvolution is the idea that not only you do your convolution, but if you have a specific response map, you would like to know, hey, this response and my later stage of my convolution, what does it look like? If I go through all these kernels one after another, like back, what kind of object is it looking like? And so this is looking at deconvolution, and there's some tricks to be able that when you do the learning to be able to do the deconvolution. And that's exactly from that paper, taken from that paper. But then there was some really nice trick from CVPR 2016, which said, okay, train your normal classifier. You don't have this part here. Train the normal CNN. But then before, and instead of using the fully connected layers that you normally have, I'm going to force you to have only one layer, and I will force you for this layer to be linear. What is nice with this is that suddenly I will have a linear mapping between class label and different response map. And so I will know which response map was useful for which. And then I can go and do the deconvolution. And so that will tell me for each of my label, what part or what region of the image was the most useful. And then they went a step further and look at a gradient-based version of that. And that's what one of the reading papers that was there. And that was, and the advantage here is that it doesn't need to do that assumption, but it's through the gradient that you will find out which layer was the most useful. And I'll let you look at it for more details. So the extension, now CNN is the basic building block. There's been a lot of extension to do this. In practice, if you have a CNN and it was trained on very well and specific object like TV, person, people, then the way to run it, a simple way to run it, so I have my object detector, and then you could detect and run it everywhere on my image and get all of these detection. And then there's been some approaches that were done to try to reduce the number of detection to only one of them. And so there's been some work, and also there's some work on segmentation. This is a picture, I don't know why the link is not showing, of like doing both segmentation and detection at the same time. But when you do object detection, one option is to slide the window, like detecting for all possible objects, but this is a very time consuming. And so there was a really neat how to do it efficiently. And the idea here was to do image superpixel. And the intuition there is if you have pixels that look the same, you should be able to take that information and be able to use that for merging. Also, sorry, the earlier citation is here. This is the earlier citation that we go. But the one that has been in a lot of papers we're using until recently is called RCNN. And here is you select 2000 region, and then and so you kind of have an initial step, which can be time consuming, but we'll discuss that in a second. But you have a fast way to find if there's an object there, and then you're going to run your fancy CNN only on that smaller object regions, and so the CNN is the expensive thing. But then I will have, and we'll talk about different ways to make this efficient, but I will have an initial one that goes over and find region proposal. So you have two steps that are confusing, but if we can get the first step efficiently, hopefully we can make the second step. It's not going to be too much of a problem. So the fast RCNN applies CNN only once, and then extract the region. And then there is a fast RCNN that do region selection on a ConvNet response map. And so instead of doing it on all of it, it will do it only on the response map. So you have a lot of these extensions. Now these days, I don't think this is completely up to date. And then you have the YOLO version 2, and there's many of these YOLO. A lot of these trademark is like precision versus speed. And the goal is to be as efficient as possible, as well as doing. So this is the idea, and that's why many of the algorithms you will see are using some extension of these region-based detectors, because they will allow you to very nicely and efficiently take an image. You get a list of objects. And then for each object, you run your CNN, and then for each object, maybe you do classification, but for each object, you run your CNN, and then you get this representation of that object, that like vector of 3000. And so you can have a list of these different 3000 vectors, and that could be a representation of that image. You could go a little bit more fancy, and instead of using not only every object, but also looking at the segmentation, looking only at pixels that are unique to that object or specific to that object. I just wanted to share that. Okay, I was rushing a little bit through that because I want to get to that last part, which is quite interesting, and I want you to think about it. And also a very nice link with the next lecture, which is about sequences, because language is a sequence. But vision is also a sequence often because you have videos. And so I talked about how to do it for one image, and you can imagine doing CNN on each image. But how do you represent a video sequence? And one of them is RNN, and or even now these days you could do self-attention and transformer, but we'll talk about these on next week, on Thursday. But another way to do it is to learn a 3D CNN, because I told you CNN can be applied on an image, or could it be applied like a colored image where it's like an image and then R, G, and B, and so you have 3 images all together in a tensor. So then there's nothing that stops you to make it a 3D tensor. If they're colored image, it would be a 4D tensor, just a little note. And it's important because when you do that, then what will be these kernel will learn? It's important to think about it. What they will look at local change of appearance. The kernel will be now a 3x3x3, or it will look at part of it will be local appearance of each image over time, like each image how they appear. But because the kernel is also 3D, like also over time, it will also look at changes of appearance. And I talked quickly about optimization, about optical flow. But these 3D CNN are probably looking at these local change of time, local change of appearance over time. In reality, what it's possible also is that they don't look at local change, but each of them are just reinforcing each other. In which case, you're kind of wasting probably thing, because you're using a 3D CNN when in fact a 2D CNN will be sufficient, because maybe to recognize a basketball player, yes, you want to see them more with the motion, but probably if you pick up their jersey or the ball or something, that will probably give you the appearance. So 3D CNN are useful in some cases, but some other time they may be an overkill. And you could imagine, I don't know if they've been, but you could imagine hybrid approaches where most of your kernels are 2D, because maybe most of your information can be done from appearance of the objects. But then you add to the also maybe some 3D that look at temporal. That may be a more efficient way. There is also the idea of doing convolution over time. And I like to talk about this mostly because it's really important to look what was the date on this. And this is one of our own like CMU faculty. But the time delay neural network was that like 1D convolution over time, although it was only done in 1D, and then later on was done in 2D, and then the name convolution neural network came in. But the time delay neural network, which happened either before or around the same time as the CNN came, was also, so the 3D CNN is kind of doing, could be used as it, and you could do it a convolution over time. And so using this idea of convolution over time, you can take a sequence of image or sequence of words. In this case, you could imagine using a CNN, like 2D CNN, get the appearance vector for that 2D CNN, do it again 2D, and then on top of it, have a 1D convolution. And a 1D convolution, what it will look, what's a 1D convolution? Any convolution, when you look at it, what it looks at templates, it look at a pattern. So what it will try to do, if you do a time delayed neural network on top of like a bunch of 2D CNN, what it will look at a pattern. If your kernels here is size 3, it will say, given those 3 images, is there any kind of patterns that's related to my loss function, like maybe detecting sentiment? And so that's what it will do. It will look at patterns and template. That's what it will look at. And so the temporal convolution network is extending this kind of idea, intuition, and just like saying, hey, I have an image and I will learn a convolution kernel, and then this convolution kernel will be run over time, will give me my response map, and that can be pooled together and then repeated again, and that can be multiple layer of TCN, the temporal convolution network. And so the temporal convolution network is an example of taking this concept of convolution, but not doing it just over the image. This one, in fact, presupposes that you have already for each image kind of got already a feature vector here. And by the way, if I give you a video like this, and I ask you, hey, learn emotions, let's say. One option is to take each of these images and run it through a CNN, like VGG face or something. But you have to remember that there's a lot of subtlety, and a CNN may return like a 3000 vector, 3000 value vector. So it's a very still high dimensional. So you want to maybe look at other approaches. I told you about these software like OpenFace that look at facial expression. So the vector here representing that image could be just the output of which facial expression are there, or where the person is looking, or where is the head gaze. And I could have, or it could be a CNN. You could go also that way. Another thing to remember, when you have a VGG net, or any of those CNN, a lot of them are trained to differentiate a car from a person, like it's object detection. What it means is that it differentiates object. It's not like a generative model in that sense. So what the issue with this is that it will learn kernels that best differentiate the different classes. It will not learn to model the different type of cars. And so a CNN, the by default CNN, may not be really good at differentiating like a red car, a blue car, like it may not be so good at differentiating different type of car. Or in the case of a face, if a model was trained for face recognition, then the goal of face recognition is to know the identity of the person and to ignore, to be invariant to the facial expression. But if your goal is to do emotion recognition, using something that was trained for face recognition may not be useful. Maybe the first few layers will be common, but the last few layers are not really the most useful. And so that's why you will maybe need to do fine tuning, because the last layers are not going to be useful by themselves. Okay, a little side note I wanted to share on this. And the TCNN, which we will talk a bit later, was learned in an autoencoder perspective.